looking at page 11, these are just some problems that involve us applying some of the rules that we talked about on the previous page. Right? So it's really just a matter of categorizing the integrand, which is the expression contained within the integral, appropriately. Right? So taking a look at number 1, I see a 1 over x to the 4th. That's an awful lot like a power relation if that 1 over x to the 4th was written as x to the negative 4th. So we would be saying here the antiderivative of x to the negative 4th dx. Right? So by rule, we would increase the exponent by 1. Now there's that understood coefficient of 1 in front of the x, so we'll divide that understood coefficient by the new exponent. So we would end up with a negative 1/3, and then we would just throw on a plus c, that integration constant. Now for number 2, it's addition, subtraction of different terms, so we could break this up into separate integrals. You wouldn't have to actually write this as a set of separate integrals. You can take the integral of each term separately. I'm just doing this at least this one time to demonstrate that there is an underlying theory that allows any kind of shortcut to take place. All right, so 3 to the x, that's exponential base a. So the rule for that is 1 over the natural log of a times a to the x. All right, so 1 over the natural log of 3 times 3 to the x. Now, in theory, each one of these would have a plus c. So I'd have a plus, I'll call that C1 because I'm going to have 4 plus c's here. Minus e to the x has an antiderivative of e to the x plus another c. X to the 3rd, that's power. So increase the exponent by 1 becomes x to the 4th. Divide by the new exponent, so that understood coefficient of 1 gets divided by that new exponent of 4. So 1/4 x to the 4th plus c sub 3. Now, the last part is kind of, it's my version of a trick question, which is to say that don't expect me to be too tricky when it comes to the way I design questions, because if this is what I can come up with when I create a trick question, then it's like the equivalent of a dad joke. It's not. It is what it is. All right. So the idea here is for you to see the e and think, oh, this is an exponential, like e to the x, but it's not, because it's not a base of e. All right. It's x to a numerical power. So this is more like x to the 3rd than it is like e to the x. So this is a case where you increase your exponent by 1 and divide by the new exponent. So we have the understood coefficient of 1, so plus 1 over, if I increase e by 1, that's just going to be e plus 1. I mean, you could say it's about 3.718, but I mean that's not as clean. So x to the e plus 1 plus, I'm going to need a little more room here, plus c sub 4. Now, what I can do here is consolidate all of these constants, right? Because if you add constants together, all you're going to get is another constant, right? So when I clean this up, I'll get 3 to the x. I'll write this as, just to make it cleaner, over ln of 3 minus e to the x minus x to the 4th over 4 plus e to, x. You see the trick question that tricks the trickster. And then I'll just say plus c, some constant c, where c is the sum of c1, 2, 3, and 4. Right? You wouldn't actually have to show that, the C1, 2, 3, and 4. It's assumed that it's going to collectively give one constant of integration. All right, but I figured at least this one time I would just show it in its full glory. All right, number 3, antiderivative of cosine is sine. All right, but before we get into that, we may want to factor out the 5. All right, you can kind of work with it as is, but we do want to get in the habit of sort of manufacturing a rule from something that doesn't necessarily follow a rule. So 5 cosine x isn't a rule, but if I pull out the 5, it becomes a rule. Right? So because we'll learn down the line in the second unit integration by tables, and this kind of leads into that idea. So antiderivative of cosine is sine x plus c, and that's going to get multiplied by the 5. If you distribute the 5, you're going to get 5 times the sine of x plus 5 times c. So 5 is a constant, c is a constant. If you multiply two constants together, you're going to get just another constant. All right, so I would just say plus c. All right. So you wouldn't write 5c because that's c, or actually integration constants are what we call absorbing constants. They're the type of constants that absorb other constants. All right, so like the Blob if you're into 80s horror movies. Number 4, which really isn't too horrible these days. Number 4 is a differential equation. We don't do much with differential equations in this course, but I figured I would at least kind of give you a taste so that you see what you would normally start with in order to end up with an integral that you would have to integrate. All right, so dr d theta is equal to pi. So if I multiply both sides by d theta, because remember, dy dx, dx dy, dr d theta, whatever, it's notation, but it's also a ratio. All right, so I could say dr is equal to pi d theta. All right. So I'm going to perform an operation on both sides of this equation. This is a differential equation. It's in differential form, right? Because we have the product of some expression multiplied by that infinitesimal change. All right. But the operation I'm going to perform on both sides is to integrate. All right, on the left, I just have a dr, but I don't really just have a dr. There's an understood 1 there. All right, the antiderivative of the constant 1 under normal circumstances would be an x, but because the variable of integration here is r, it becomes an r. All right, but we're going to have a c, all right, because we do have an integration constant. All right, now the pi is a constant value like k on the previous page. The antiderivative of that normally would be kx plus c, but the integration variable here is theta, so in this case it would be, and the constant that's given is pi, so it would be pi theta plus c. All right. Now these are two different c's, or more accurately, two c's that are not necessarily the same. So if I were to subtract the c from the left and bring it to the right, it wouldn't necessarily cancel out. It would just give us another constant. So I can actually perform the operation of subtraction. But just like here, when I added all these constants, and all I ended up with is one other constant that absorbed all the others, that's the same idea is going to be in play when I subtract. All right, so I'd be looking at r is equal to pi theta plus c. All right. Now numbers 5 and really on, they go back to kind of rules-oriented expressions, but sort of disguised. All right, we don't need anything more advanced than the rules that you see on the previous page. All right, so that's something to keep in mind. All right, very, very important, because when you're integrating, and this is kind of like my stock phrase when it comes to this course, is you want to be working from the beginning of the course to the end of the course. All right, if you see a problem, if you see an integral problem, you want to work with the simplest approach first. Try that, because it's usually going to be the easiest way to go. Look for a rule, essentially, and then start getting more and more complicated with your approach. Right? In this case, I'm looking at it and say, well, I mean, if you have experience with integration, you might be like, oh, well, is it partial fractions? Is it something like that? Well, let's try something basic. Well, I see a sum and difference in the numerator of a fraction, which means that fraction could be broken up into different parts. So let's do that. X squared over x to the fourth plus 2x over x to the fourth minus 3 over x to the fourth dx. Now, in the second example, I showed you that when you subtract or add within an integral, that all you're really doing is breaking up the integral into separate integrals and then combining all the integration constants down the line. The moral of the story is here we don't really have to break it up. We can work with it as long as we throw a plus c on at the end. All right, so I'm going to write this as antiderivative of x to the negative second plus 2x to the negative third minus 3x to the negative fourth dx, and then integrate each part. All right, increase the exponent by 1, becomes x to the negative first, divide by the new exponent. Well, that's going to become a negative. 1 over negative 1 becomes negative 1. Increase the exponent by 1, divide by the new exponent is going to become a negative 1. Increase the exponent, sorry, I'm just cleaning that up. Increase the exponent by 1, divide by the new exponent, that's going to become a positive 1. And then we just throw a plus c on at the end. All right, so just using the reverse of the power rule gets the job done. So along the same lines, in number 6, we could look at each part separately and say, all right, what do I know about the antiderivative of x to the second? Well, it's a power expression, so increase the exponent by 1, divide by the new exponent. Secant squared, that's actually a rule. Antiderivative of secant squared is tangent, so plus tangent x. Just don't forget that plus c. All right. Now, in an online course, online, in person, there's always different ways things play out. In an online course, you'll have fill in the blank questions on tests, you'll have multiple choice questions, and so on. In an in-person course, you'll have, pencil paper type tests. Bottom line is, regardless of what type of test you're taking, there's going to be situations where you'll have the need to find the antiderivative. And when you do, you're either going to remember to put the plus c or not. I can tell you that there will be a point deduction in some capacity, regardless of what kind of course you're taking, anytime you forget a plus c. All right? It's that important. All right? We're not really at the moment in the course where we get to why it's as important as it is, but it is incredibly important that you remember the plus c. All right, so every time you forget it, it's going to cost you. So be very, very careful about that. All right, number 7, I'm going to rewrite first. X to the 1/2 plus 1/2 x to the negative 1/2. So just a rewrite first. Then increase your exponent by 1. All right, so 1/2 becomes 3/2. Divide that understood 1 by the new exponent. 1 divided by 3/2, keep change flip, becomes 2/3.
x to the 1/2.
Instead of negative 1/2, negative 1/2 plus 1 is 1/2.
Take that positive 1, divide by the new exponent, gives you a positive 1, plus c.
Now, number 8, you might look at again if you have some experience with this course content. You know, maybe you took AP Calculus in high school. Maybe this is your second go-around with this course. Whatever, you might kind of get in your own way in terms of what you already know. Work from the beginning of the course to the end. First thing I see here is a binomial squared. All right, I look at that and I say, well, in Algebra 1 or college algebra, whatever course you took, we learned that you use double distribution or the FOIL method to expand that out. So why not do that here? All right, so this is the same as saying 2t squared minus 1 times 2t squared minus 1. So 4t to the 4th minus 2t squared minus another 2t squared, so minus 4t squared plus 1 dt. Now it's a power relation. So increase the exponent by 1, divide by the new exponent. Increase the exponent by 1, divide by the new exponent. Now this one doesn't seem to have an exponent, a variable with an exponent. It is a 1, so you could say it's a t, but I kind of alluded to this on the previous page, but I'll say it explicitly here. You can assume that it has a t to the 0th here, in which case you would increase your exponent by 1 and divide by the new exponent and still come up with the same result. All right, so it's a little bit of a justification for why that 1 becomes a t. All right. Numbers 9 and 10 both involve natural logs, but they're actually not too bad because they're rule-based. The first thing I notice in the case of number 9 is I got a power on that log, and what we can actually do here is use the power rule for logs. Old pre-calc topic. All right, so the power becomes the coefficient. So we have the 2 that's already there, but this 2 will become the coefficient of the logarithm. So 2 ln x dx. Now that 2, the one that's the coefficient of the log, can now be factored out and multiplied by the 2 on the outside. And so we're at the point here where all we would need to do is find the antiderivative of the natural log of x, which at this point is just a rule. So 4 times x ln x minus x plus c. So I would just run through with the 4. So 4x ln x minus 4 plus 4 times c. Constant times constant is a constant. For some of us, that's going to take a little getting used to, but that's the way of it. Now, the last one's actually pretty not bad because we still have that power rule for log thing going on. The exponent could become the coefficient. There's also a way around that if you don't like that, but for now we'll just say this. The natural log of e is actually equal to 1. So we're really looking at something that simplifies down to 2 times the integral of x. The integral of x, increase your exponent by 1, so x squared, 1/2 plus c, then multiply it by the 2, and you get x squared plus c. All right, so kind of a simple answer compared to what you might have started with. But another thing you can keep in mind is that there is a rule, a pre-calc rule, the natural log of e to the x is equal to x. All right, and we talked about this one already, e to the ln of x, on the previous page that is equal to x. So these are rules. So you might want to hang on to those because they're helpful. Little bits of time savers.